Okay, this is EENG 360 Hardware Description Languages, and this is part 3 of Lab 6. In part 1, we stubbed out the code. We had 50 million clocks that we were waiting, a little timer down here, our usual state machine. You need to go back and watch parts 1 and 2 if you haven't watched those yet. And then we came along and did a test bench file. But the thing that was of interest here is that we use that generic to override DVSR and set it up to maybe like 4 clocks so that we could actually see it on a simulation screen. Well, now that we've got it working in simulation and we're confident about that, we want to go over to implementation. So let's go to the left half of the screen, and notice you've got your component and your test bench file. It's currently selected for simulation, the radio button here. If I click implementation, well, that test bench file disappears. Well, that makes sense. We're implementing. There is no test bench file. But what we do need to add now is we need to add a constraints file. So let's call this user constraints and make sure it's a constraints file. Next, finish. And now I've got my component with a UCF file. And what I need to do is I need to map all the inputs in my entity. Well, let's go back and look at my entity. The entity on the super register consisted of all these signals here. Clock, synchronous clear, load, enable, down, D, reset, max tick, min tick, and Q. So we've got to map those to actual physical pins on the Spartan 3E. Okay, well, open up your UCF file and basically go to that document that we have on Canvas that talks about all the pins, and insert that into here, and I'll just paste it in. We're going to use the 4 switches, L13, L14, H18, N17. Those are actually labeled on the chip, and then that's going to be my D input, D3 through D0, and then I'm going to use the LEDs. The first 4 LEDs, F12, E12, E11, F11, are going to be my 4-bit counter, Q3 through Q0. I'm not going to use the next 2 LEDs, so I have those commented out. Then the 6th LED is going to, or the 7th LED is going to be min tick and then max tick, and they'll be at E9 and F9. Now we're going to use the push buttons, okay, and H13 is the east button. That's a comment over here just to remind me. V4 is the north button, K17 is the south button, and D18 is the west button. And I'm going to map those to the variables synchronous clear, load, enable, and down. Now I also want to use the push button rotary. So that guy corresponds to V16, and I'm going to use that for my asynchronous reset when we push down that push button. Now this is going to be driven by a clock. So I'm going to call the clock variable clock. You can call it whatever you want. My clock, clock 1, clock 2, whatever. It's a variable name. That's what we called it in the entity. It's located at C9, LVC MOS 33, period 20 nanoseconds, 50 megahertz. And I'm not sure about high. I think that's duty cycle right there. I'm not sure. But I just leave it alone. Use the default values. So at that point, we save it. Okay. So then we kind of open up our window here, and we go through the process for putting something onto the board. And first thing we do is we open the synthesize node and double click on check syntax, and then we just let our computer crunch. But notice, I didn't do one single change from what I was using in the simulation. I'm using the default value of DVSR in my generic. So nothing has changed when I switched from simulation to implementation other than me adding a UCF file. Then I need to implement design. You can right click and say rerun all, and it'll translate, map, place, and route. And you get a bunch of output down here. Keep an eye out for errors. Alright, we did that. Let's do a generate program file. Double click on that guy. Generate the bits that we're going to download. And Okay, and then the next thing is to open up the Configure Target Device node, and you want to double click on this impact one, Manage Configuration Project. That process is going to bring up another window. And let's see, let's kind of maximize that guy. Double click on Boundary Scan, right click, Initialize Chain. It'll show you 3 chips here. First one is the FPGA. The other 2 we're going to bypass. We're not going to do anything. Do you want to continue and assign configuration files? Yes. We want to pick a file that's going to contain the bits that we're going to put on that first chip, the XC3S500E. Okay, so I need to browse to where this stuff is located, and I think this is located in Lab 6 Demo, and there is Super Register, the name of my component, .bit. Okay, there's all my bits. Now I don't care about doing anything with this flash prom. So I'm going to say, do you want to attach? No. And then here it's asking you, what do you want to do to this device? Do you have any bits for this device or the next device? No. So I'm going to choose bypass. And now you'll notice the next device is highlighted. Well, we're not going to use that one. And then here you've got your devices. The XC3S500E is an FPGA device, specific programming. FPGA. The second device is a PROM, programmable read-only memory. If you actually wanted to burn your program into ROM and have it boot from ROM, then your program would stay on the board when you took away power. Because now if you take away power, it's going to be erased. But we can burn it to PROM too. And then there's a CPLD. CPLD stands for Complex Programmable Logic Device. And it's similar to an FPGA, kind of like a complex PLA or a PAL. Right? So at that point, just click OK. And then here we select that first chip. Notice, you can select each one, but you select the first one, make sure it's highlighted. Right click Program, and I should be downloading bits over the USB, and you don't have access to a board, but if I reach over here and I exercise my board, yep, things are working just fine. Okay? And we are good. So I'm going to pause the video. No, and I think we are done. That concludes part 3 of Lab 6. See you next time.